So what we just covered were several different masks that were needed in order to generate a simple inverter on an integrated circuit chip. So basically, summary is IC chips are specified or created using a set of masks, and you have to generate those masks in order to go into a fab facility and create a IC chip. Now, the minimum dimensions of those masks, so the smallest spacing between different sizes and the minimum dimension in particular of the gate size for a transistor determine what the transistor size is. And in general, the smaller the size, the faster the speed of the transistor will be, the lower the cost, because the more transistors we can get on a given wafer, it tends to be lower cost. And if we're not increasing the frequency, generally as we reduce the size of the transistors, we can wind up with lower power as well. So the feature size for a transistor, or the minimum feature size for a transistor, is F, is the distance between the source and the drain. So it's the length of the gate of the transistor. And this is set by the minimum dimension or width that you can draw a piece of polysilicon on a given process technology. So generally the feature size improves currently about every 30%, every 3 years or so. It will reduce by about that much. And the other thing to keep in mind is once we have a minimum feature size, it kind of defines what the minimum distance between various different mask layers is allowed to be. And as we so the gate might have a certain minimum design size, but the metal that's above that would be the first layer of metal, might not necessarily have the same minimum size. It might be slightly larger. Generally it will never be smaller than the minimum size of the gate. But generally for a given process technology, the minimum gate size kind of describes the process technology minimum rule, which is that feature size F. And as we try to determine what the rest of the minimum distances that are allowed for other layers of the metal, the polysilicon, the vias, and as we go up in metals, we'll have metal 1, maybe we'll have another metal on top of that, metal 2, and we'll have multiple layers of metal in order to get all the interconnections that we need. And all of those design rules will be in terms of what's called lambda, and lambda is F over 2. So as we talk about how to do layout in the coming lectures, we'll be talking about design rules for that layout, because you have to construct it in such a way that it's legal to fabricate. And we'll be talking about those design rules in terms of lambda. So in a 0.6, for example, 0.6 micron process, the value of lambda would be 0.3 microns. So here is just a very simplified example of some design rules that you will have on a fabrication process. So you might have a metal process where you'll have like a metal 1 and a metal 2, which will be a layer. Once you put down your metal 1, you'd put some silicon oxide over that and then define a second layer of metal over it, such that you can have more complex interconnect, similar to like a PCB board that has multiple layers of metal, to be able to have more complex interconnections. And just as an example, Metal 1 might have a minimum spacing width of the metal itself, can't be any narrower than 4 lambda, and it might be the distance between one piece of metal and another piece of metal can't be any narrower than 4 lambda, just as an example. Another design rule that you might have if you look in the lower left is when you're making connections to your metal, you have to make sure that the via where you're cutting out material in order to make contact between different layers, you need to overlap that via with metal and have enough overhang such that if the metal doesn't completely line up with the via, you don't want it having a short or an open. You don't want to, if you just had the metal exactly over the via and there was a little bit of shift in lining up your mask layers, you could have a complete open and you don't have a connection to the metal. So you need to overlap the metal, and so that overlap width or distance might be 1 lambda, for example. And for your actual contact itself, so the second thing from the left, in the bottom left, it shows a 2 lambda. That's the actual size of the via itself. That contact is saying it needs to be 2 lambda, for example, in this particular process that we're given an example of. Then there's also what is the minimum space that a given via or contact can have to another contact. So if we're looking on the kind of the bottom row there, the third one from the right is saying 3 lambda. So you can't have one contact closer to another contact than 3 lambda apart, because otherwise those contacts might accidentally get too large and possibly short to each other or do something. And some other examples on the top row, if you're looking at your diffusion for whether it's N diffusion or P diffusion, the minimum width or one side of the diffusion would be 4 lambda, and the minimum spacing from one diffusion to another is 4 lambda, to make sure they don't contact each other. The polysilicon, we already said that the minimum feature size is generally the width of polysilicon, which would be F, and F was defined as 2 lambda. So in general, the minimum polysilicon width can be 2 lambda, but then if you have polysilicon routing next to another polysilicon in this process technology, it can't be any closer than 3 lambda apart. Then a couple other design rules that are shown on the right hand side here are inside the N well. The spacing between diffusion, so if you have a PMOS transistor defined for P plus diffusion, the N well has to be wider than or overlap that P plus diffusion by at least 6 lambda extra. And then if you have a NMOS device outside of the N well, so N plus diffusion, the minimum spacing for that NMOS transistor, N plus diffusion, has to be at least 6 lambda outside of the N well. It can't be any closer, otherwise you might accidentally have your N plus diffusion start shorting to the N well. So these are just a few of the various design rules. The last one that I see on this slide is on the more upper right. There's a 2 lambda, which is showing how much the polysilicon has to make sure it goes beyond the N plus or P plus diffusion by at least 2 lambda to make sure it fully covers that diffusion and you don't accidentally get a short at the very edge of your diffusion where the 2 diffusion layers are shorted together through, if that, like let's say that polysilicon shifted down by more than 2 lambda, you would actually have N in the top there, you'd have P plus diffusion that would actually short the source and drain together, and you wouldn't have a gate over it. So you need to make sure the gate overlaps and goes beyond the diffusion far enough so that the gate fully covers all of the diffusion. So those are just some of the design rules. There's a lot more than just this, but this is just an example. Now that we know how transistors are fabricated, let's go back and talk a little bit about specifying the dimensions for our transistors. So transistor dimensions, if you remember back to previous classes, we have the length of the transistor channel, but we also have the channel width. The minimum feature size, as we talked about in a couple of the previous foils, minimum feature size is defined as the minimum length for the channel, which is the minimum width that we can make the polysilicon layer, and that's 2 lambda. In general, for the many processes, the minimum feature size for the width of the transistor is going to be twice that. So it's going to be 4 lambda for the width and 2 lambda for the length. And usually we do width over length because that's how the current equations go for the transistor, is W over L. And so sometimes we'll call that the 1 unit, or a single unit is the minimum size for the transistor, which would be 4 lambda over 2 lambda in this case. So in a process where the minimum feature size F is equal to 0.6 microns, this would mean that the minimum transistor would be 1.2 microns wide and 0.6 microns long. So down below, there's 2 circuit diagrams shown. One that's showing if you had a PMOS and NMOS transistor connected together for an inverter. It's showing where if you had a PMOS device where it was 8 lambda wide, so twice as wide as the minimum that's allowed, and 2 lambda long, connected to a NMOS transistor that is the minimum size of 4 lambda wide by 2 lambda long. And that's showing width versus length of those transistors in that circuit diagram in terms of lambda. And then the right hand diagram is showing if you showed that same circuit in terms of what the units are. So assuming that it's 2 units, the PMOS is 2 units wide, and assuming a minimum length, and the NMOS is 1 unit wide with a minimum length. Typically, in a lot of older processes, the reason you might be wondering why the PMOS is being shown as twice as wide as the NMOS, and the reason for that is in a lot of the older processes, if you go back 20 plus years, the PMOS devices tended to be half as strong, or in terms of, if you go to mobility, the PMOS mobility was half as much as the NMOS mobility. And so if you wanted to have equal drive strength of your NMOS and PMOS devices, you would have to make your PMOS device twice as wide as your NMOS device to keep it approximately the same drive strength. And so that's why you'll see throughout a lot of the circuits, the PMOS will be twice the width of the NMOS. In more modern processes, they found ways to improve the PMOS device drive strength as they've scaled the transistors smaller, improve the PMOS a little bit more each generation than they can the NMOS, and so they've come closer to parity. That it still tends to be that the NMOS is stronger than the PMOS, but it might be more like a factor of 1.5 or lower in modern processes, maybe down to 1.2 or 3. So you might not see as much discrepancy if you're looking at a modern process technology. So hopefully this short introduction into layout and integrated circuit fabrication has given you a little bit of just respect for how difficult and time-consuming layout can be. Basically, just to create an inverter, you can see there's many different layers that you need to draw in, and you have to satisfy various different design rules, get all the sizes correct, etc. And so, basically just want to emphasize that layout can be very time consuming to do. It's one of the common things that I'll say in my work at Intel is somebody who's doing kind of the logic design, they're writing Verilog or HDL code. They can make a change in just a couple minutes that someone doing circuit design might take hours, and somebody doing layout takes days. So layout, definitely the closer you get to actual the structure of transistors and how to make them, the more time it takes. So with that in mind, as we're designing all of our layout, you want to design each individual gate so that it fits nicely together with the gates that are going to be going next to it. So typically what we do in IC design for a given process technology, when we go to whether it's Intel or TSMC or like Global Foundries now, to actually have a design fabricated for a given process technology at a given company, what you'll try to do is build a library of standard cells. And the standard cell design methodology, you'll create this set of standard cells that can be used for multiple different designs that you're going to be sending to that process technology at that particular company. And a couple things that you want to do when you're creating these standard size cells is, we saw that we had, you have a VDD and a ground that have to connect to your PMOS and NMOS devices. So typically we'll have a VDD in the cell and a ground in the cell. And you want to make sure that when you place one given cell, like an inverter, down, and you might have a NAND gate placed just to the right of it, you want to make sure your VDD abuts to the VDD of the cell next to it. And the same thing with your ground. You want to make sure your ground of one cell abuts to the ground of the neighboring cell. That way you can kind of put the cells together kind of like Legos, and they all fit together nicely. But this requires all cells to have a standard height. So the distance between the VDD and ground are usually, that's your outer top and bottom of the cell. You want to make sure that that height, that distance, is the same from cell to cell. And you also want to make sure that adjacent gates will satisfy all your design rules. So if you place one gate by itself, should satisfy all the design rules, but if you place another gate right next to it, you want to make sure that it's correct by construction and still satisfies all the design rules. So typically what we do is we put the NMOS at like in the bottom of the cell, the PMOS designed along the top of the cell. That way all the PMOS will be next to each other. All the N wells that the PMOS are in will align with each other along the top, and all the NMOS will be along the bottom. And if you make all your gates include your well and substrate contracts, then it will all be correct by construction, and you won't have to worry about missing out on those contacts as well. So this kind of shows an example of what I was talking about in the previous slide, where we have an inverter here. We do have some space between the PMOS and the NMOS. The PMOS is surrounded by an N well, needs to be enclosed by the right amount of distance on either side of the P plus active The end well needs to enclose it by minimum DRC on every side. And then outside of the end well, we have the N plus diffusion for the NMOS device. That needs to be a certain distance from the end well. There's a minimum DRC for that. And so the A is showing if you don't actually have well and substrate tap included in your standard cell. And the B1 is showing if you put a well and substrate tap inside of your standard cell. Now, the advantage of putting a well and substrate tap inside every cell is that you never need to worry about having enough of them. And because there's a certain minimum distance that you can go between any well tap or substrate tap. You can't go too far in distance before you need to, you're required by the process technology to have a substrate or a well tap every so many microns. The disadvantage of putting it inside every single cell is that it kind of wastes area. You probably don't need it all that often. So there's other alternatives that we can get into in the future where you might not include it in every single cell, and you might create a specific cell that you place every so often that includes a substrate and well tap, but we can get into that more in the future. So here, just wanted to show a more complex layout than we've seen before, and we'll look at this in order to determine, okay, how large would we need to make a particular standard cell. We need to figure out what would be the X and Y dimension that you'll have to take up in order to design some of your more complex standard cells. So here in the horizontal direction, you can see a lot of the determining factor of how wide your gate or how wide your standard cell is going to be has to do with how many inputs do you have. In this particular case, for a NAND 3 function, you have an input A, B, and C, which means you have 3 polysilicon gates. And then you also need contacts on each side of each of those polysilicon gates. So in this particular case, you need 3 polysilicon. You need the distance on each side of those polysilicon for 4 contacts to the diffusion, the P diffusion underneath. Then you need distance of the well that has to overlap that full PMOS or P plus region for the PMOS transistors. So adding up all of that, the polysilicon, the contacts plus the well overlap of all that will give you the minimum horizontal distance. The minimum vertical distance will be basically your P plus diffusion for your PMOS. The contact, in this case, the well contact, has to be a certain distance away from the P plus. You need the N plus, and then you need the N well to overlap on the N plus side on the top. You need the M well to overlap the P plus PMOS device on the bottom by whatever the distance the DRC requires. Then you need the distance between the N well and the NMOS N plus diffusion. And then after that, you need a P plus contact to your substrate at the bottom, and add all that together, and it gives you the minimum distance for the vertical distance of your cell. And so adding all that up, you can get an idea of what your minimum X and Y of this particular cell in the layout. For this particular case, it's 32 lambda by 40 lambda. Now, you can see that trying to lay out all of that every single time in order to get your minimum X and minimum Y could be a lot of work. So one of the ways that we can try and simplify this is doing what is called stick diagrams.